Hello and welcome back to another CS224 screencast. I'm titling this video From Small and Simple Things, and I think you'll see why in a moment. The purpose of this particular screencast is to try to establish kind of a framework of thinking that I believe will help you to assimilate the information that we're going through in Chapter 3. So as I've looked at the book, I feel like that the coverage of the technical information is actually pretty good, especially once you get used to the syntax that they're using. I feel that the greatest struggle for many of you is probably going to come with wrapping your head around this kind of bottom-up approach. Okay, so we've been working with computers and high-level programming languages for so long, we're so accustomed to abstraction that now we're kind of looking under the hood, and it can be bewildering to see all of these little moving parts. And so I'm hoping that with this presentation I can suggest to you both explicitly and implicitly a different way of thinking. Okay, instead of kind of thinking from the top down and trying to immediately relate the things that you're used to these new things you're seeing, I'm going to suggest that instead we try to look at these small pieces in their own right, understand them, and then try to work upwards towards the things that we're already familiar with. Okay, that gives us a little bit of context. Also, understanding that this is what happened historically can help us to realize that many of the things that we work with are the result of decisions that other people have made based on common sense, or in some cases simply expediency, whether that be financial or strategic and so forth. Okay, so let's jump in. Now here's a quote from Alma chapter 37. Now ye may suppose that this is foolishness in me, but behold, I say unto you that by small and simple things are great things brought to pass. And small means, in many instances, doth confound the wise. In no technical field is this truer, I think, than in computer science, or at least once we start looking at it, in no other field is it more obvious. Okay, so computer science, and I would argue that engineering in general, is very much the art of composition. We start with small and simple things, and we put them together in intelligent ways, and the end result is a much more complex and powerful effect than you might expect that we could get from such simple beginnings. So it's not intuitive, but it is very powerful. Okay, so with computers, obviously, then it all starts with a bit of data. Har, har, har. There's my pun for the day. All right, so, but really it does, right? So we discussed in a previous screencast the fact that kind of at the base of digital computing is this idea of a logic gate, a 1 and a 0, and using these two things to form binary values, and then interpreting those values in different ways in order to perform computations on these symbols, symbolic computation, if you will. So we start with very simple logic gates, and if these are confusing to you, you may have missed a screencast, so go back and look for the one on binary circuits. But suffice it to say, we begin with very simple circuits, switches, and automatic switches. Then we organize those simple things into these logic gates. So we literally start with the ability to turn something on or off, and to do so automatically. We build up to this concept of a logic gate. From there, we can build more complex behaviors such as the XOR circuit, or XOR gate as it's often called. If we were to look inside of an XOR gate, we would find a bunch of switches implementing something equivalent to a combination of logic gates. Okay. Now, excuse me, in that same screencast, we talked about the fact that an XOR gate comes close to doing addition. It does 1-bit addition, right? If I have 1 and 1, I get a 0 in that first bit position. Why would that be appropriate? Because 1 plus 1 is 2 in binary, which is a 1 followed by a 0, right? So we get the 0 correctly. 0 on either one of the inputs and a 1 on the other will give us a 1 with an XOR gate. Okay, so 0 plus 1 is indeed 1. All right, so an XOR gate mimics some of the behavior we'd expect when we're performing addition. And we saw that if we add an AND gate on those inputs, then we can create basically a 1-bit adder without the ability to handle a carry in. So now we have the carry out, so we get the 2 bits, the S bit being the least significant bit, and the C or carry bit being the most significant bit. of adding two 1-bit values together. So again, this is just a review. If you need that, if you need help understanding that, come talk to me or one of the TAs. I should say, talk to your instructor or one of the TAs, or view one of those previous videos. Okay. Then we go from this half adder, and notice in this half adder we see the XOR gate embedded within it, and then we can go to full addition, wherein we handle both a carry in and a carry out, as well as the sum. And if you look closely there, then you can see within that circuit the XOR gate and the adder connected together, the XOR gate and the AND gate connected together to create that half adder kind of in the center of that diagram there. So very much we are using this idea of composition, where we start with basic things that we understand, we know how they behave, and we put them together to get more complex things that have more complex behavior. Okay? And so we can keep applying this idea all the way up to our computers. Okay, this concept is utilized from the ground up to give us these powerful computing machines that we have today. So this is not a totally new idea, right? Where things get kind of dicey is that on top of this idea of composition, we add the idea of abstraction, which is basically the art of summary, I will say, wherein instead of looking at all of the details of the particular things that we build, we look at them from a high level. Okay, we abstract away the details and just talk about this complex thing we've built as a simple entity with a set of predictable behaviors. Okay, that's very powerful because it enables us to think about things more easily. Our minds can only hold so much information in the forefront, okay, that we can actively reason about. And so by abstracting away some of the details and considering really complex things in simple ways, then we're able to think about larger ideas. Okay, and so that's what's going on here. When we look at a computer from a systems perspective, I should say a computing system from a programmer's perspective, this is closer to what we will generally reason about. We'll talk about registers as a set of things that have very predictable behavior. We won't talk about the gates that they're built out of or the technology underlying them. We'll talk about a CPU in terms of the registers, the condition codes, and the program counter, the instructions that it's executing, the data that it is using or writing, reading or writing to and from memory. I should say from and to memory, I suppose. The addresses that are generated in order to tell memory where to get things or where to put things and so forth. We might reason about abstractions within the memory itself, this concept of a stack, which is really nothing more than a way or a pattern of reading and writing memory. Okay, reading and writing values to some location that we can store memory. Okay, so as system programmers, these are the things that we'll deal with. And when we look at a computer's architecture or its instruction set architecture, this is the view of the system we're allowed to see. The instructions allow us to operate on these entities. Okay, so under these entities, there's a lot of magic. Hopefully, we don't feel like it's magic at this point. We understand that there's a machine that somebody built. But from the level we're looking at it, we just assume that's going to work properly and it will behave as it is specified. Okay? So we're then trying to work at this level where we're going to manipulate directly, for now, okay, we're going to manipulate directly things like registers and the program counter and memory locations and the data stored there. Okay, so before we jump back into that, I just want to review real quickly here and actually add a few comments to the discussion about registers. Okay, so these registers are our storage units at least they're our basic storage unit at this low level of computation that we're talking about. And with the x86 architecture, we've seen that there's kind of this nested structure. So the original x86 had 16-bit registers, and it had 8 of them. Okay. Now, you could think of this, and the book kind of suggests that we do, as an array of registers. Now, it might have been easier for us to think about this if they had simply numbered the registers and said, well, register 0, 1, 2, 3, 4, 5, 6, 7, and so forth. Then the notation in the book would make really great sense because we could think of an array of registers, we'll call it R, and an index to tell us which one. Instead, they use this notation where they say register, and obviously those are equivalent and just as useful. But we see a different naming scheme, right? So there's this register AX that we start seeing written inside. Okay, so you can think of that, though, as this index, okay, index 0 in this array. So hopefully that helps you understand, if you don't already, the notation in the book. Okay, why am I revisiting this? Well, because I've seen that there are some questions, and this isn't quite apparent to people yet. Why this strange naming convention, RAX? Here we see actually the original names, AX, CX, DX, and so forth. So why these interesting letters? Well, that comes down to the fact that the original designers were actually thinking about how they would use these registers. Okay, they were thinking about writing compilers, okay, that would directly program these registers, or programming them themselves by hand. And so they had patterns they would apply when they'd write their programs that would help them to keep track of things. And so the AX register was the accumulate register. So this is where the results of computation would generally end up. The CX register was used as a counter. The DX is a data register, okay? And so you can see that the naming kind of follows this convention of using the first letter in the word that they were assigning to the use of that register. And as is noted here, this approach is mostly obsolete. I mean, first of all, we don't tend to program these things by hand anymore. Compilers do it. And secondly, the compiler is in no way bound to the exact conventions that they were using. So it was a neat idea at the time. Now it's a historical anomaly that's a little bit confusing to us, okay? So as these registers, these original 8 registers, were extended with the 386 to be now 32-bit registers, okay? Then we just see they added an E, which I believe stands for extended. So we have this extended AX register, so on and so forth. And then this idea of virtual registers allowed us backwards compatibility. Okay, also just a quick reminder then, this lower 16 bits, okay, so this section of the registers here, okay, 16 bits were the original word size for the x86, and so 16 bits is considered a word in their vernacular, and 32 bits would be a double word, often referred to as with an L, or I think representing long is the idea there. So and if we see an L in an x86 instruction, we mean then 32 bits. Okay? All right, so moving forward then, when IA32 was extended to 64 bits, to be a 64-bit instruction set, the same scheme was applied again, where we've basically now nested a 32-bit register inside of a 64-bit register, okay? I should make it clear that that's for the whole thing. Okay, so no big surprises there. An interesting thing happened, though, when they went to the 64-bit extension, they also decided to add 8 more registers. And here we see them using actually a naming convention that may be more comfortable to us. They use numbers instead of these interesting letters that are supposed to suggest names. All right, and so they started with 8, not surprisingly, because we're computer scientists, we start counting at 0, and so 8 was the logical place to begin. So we have these other kind of general purpose registers available to us on our 64-bit machines. Okay, so again, registers are something we can see and interact with directly using the assembly instructions that we are learning. So let's try to use those and use these resources we can see to do something arguably useful. Let's compute the Fibonacci sequence. So as a quick refresher, the Fibonacci sequence is just a sequence of n numbers or n values that are computed by summing together the previous 2 values. Okay, so xn is equal to the number before it and the number before that. All right, so this sequence then could start with, here we're starting it with 0, 1. So the next value is going to be 0 plus 1, which gives us 1. The next value then will be the previous 2 summed together, which gives us 2. And then we do that again. 2 and 1, we get 3. 2 and excuse me, yeah, 2 and 3, then we get 5, and so forth. You get the idea. So this is classic Fibonacci sequence. It's not only interesting mathematically, but it ends up showing up in nature. We see it in certain flowers and the way the petals are arranged, pine cones, and so forth. So I believe it's also tied to the golden ratio, okay, as I recall. So this is more than just a novelty. This is something that has interesting mathematical properties and can show up in surprising places. So we may very much want to be able to compute a Fibonacci sequence in various circumstances. So how could we do this using then these registers that we have available to us and some of the simple instructions that we've seen so far? Well, here's an example of doing this. I'm just going to walk through it and hopefully reinforce some of the basic ideas from the book and get you thinking from this bottom-up perspective. Okay, let's use these simple things to build great things. So here I've got this hypothetical Fibonacci.s file just to indicate, okay, so these are assembly instructions. Let's walk through it. So the first instruction, move Q0 into RAX, all right? So this is simply going to write the value 0 into this register. No surprises there. Followed by another instruction that will store a 1 in the RBX register. Okay, so we're using these simple buckets that we have available to us to store the beginning of our sequence. Now, you may recall, that the add instruction, which we're going to use in a moment, will add together the value of two registers and store the result in one of those registers. Specifically, the first register is considered a source. The second register is a source of data, but it's also the destination of the result. So if you were to go look at assembly code that was written by hand, especially in the early 80s, then in general you'd expect to see RAX on the right side of these kinds of instructions because it's the accumulator. So it would be where it would be the typical destination for our results. It also ends up being the register that we're going to return values in. So when we do a bunch of work, we'll accumulate the result in that register. And if this was a procedure call or something like that, so think it was a function call, when the thing returned, it would be the RAX register that we'd look at if there was a value that was supposed to be returned from this function, okay? So, and we'll still see that in a little bit. We'll see that convention is still followed in terms of how the compiler returns values. We still use registers in certain ways. Anyway, moving on. So the point here, though, is that if I'm going to add two values and store the result in RCX, then I need the two values I want to add, or I shouldn't say RCX, in this case I'm using RCX, but more generally speaking, if I want to add two values and store the value in one of the registers, in a register, then I need one of the two values to be in the register that I'm trying to get the end result in. That probably was confusing. So let's walk through this. Here's our strategy. What we're going to do then is, since we want to add these two values together to get the third value, what I'm going to do is move the very first value, RAX's value, into RCX. So that'll be a 0. So initially we'll place a 0 in RCX. Okay, now I can add RBX to RCX, okay, which is equivalent to adding RCX to adding RAX to RBX, because you'll note then that here's the BX, and we've just copied RAX into RCX. So RCX is holding the value of RAX. Okay, so we'll sum those things, we'll get a 1, and then the result will be stored in RCX. So we now have a 1. Okay, now we'll do the same thing. We want to compute a result to store in RDX. So we're going to look back and say, all right, we were going to sum the previous value and the value before that. So we'll take this value and we will move it right here into RDX. So we'll temporarily write a 1 there. Then we'll do the add, where we'll add RCX to RDX and store the result in RDX. So 1 then in the RDX register plus RCX, which has a 1, will give us a 2, and that will be written in the RDX register. So this appears to be working. Let's move on. We'll do the same thing for the RSI register. We then want to add up, let's lock these out for a minute. We want to add these two registers. So we will move the value in RCX into RSI. Okay, so that's now sitting in RSI, and then we will add RDX to RSI. I didn't write it down. How foolish of me. So RCX was moved into RSI, so we had a 1 there. Now we're going to add then the value of RDX with RSI. That will give us a 3, and that will then be written to RSI. And we'll proceed to do this. Now we'll skip, because it's a no-no to mess around with it. With this sequence, we would have skipped the RSP register. That is our stack pointer register. And so in general, we want to leave that alone. But if we'd continued this all the way down, finally we would have computed the value for R15 by first moving the value of R13, okay, into R15, and then adding the value in R14 to the value in R15 and placing the result in R15. And then we would have been done, okay? Now, so you can see here that we could compute several of the values of a Fibonacci sequence just using these registers. But now what, right? So we're out of register space. What can we do? So using registers in this way is only effective for a short time. What we want to do is figure out a way to reuse our registers when we're performing computation. So how do we do that? Well, a simple way with this Fibonacci sequence can be demonstrated thusly. Let's put our 0 and 1 in registers RAX and RBX, just like we did before. And then we will simply say, well, let's add RBX to RAX and store the value in RAX. So we'll call this N0, we'll call this N1, and this will now be N2. Now notice then that N2 is going to be the result of summing N0 and N1 and sticking it in N2. N2 is going to be RAX. Okay, so we're overwriting the value in RAX with the new sum. Okay, so we're reusing the register. Now we can do the same thing again. This time we'll take the value in RAX and add it to the value in RBX and store the value in RBX. So if this was N0, this was N1, and then we put N2 into RAX, we now have N1 and N2 in RBX and RAX. We add them together again, and we get N3. Now, you might have observed that it actually, well, we'll just go on from here. Okay, so by alternating these things, then we can continue this pattern, and what we're doing is we're overwriting the value in RAX or RBX with the next value in the sequence. We then still have the previous value, right? So we had N0, then N1, then RAX gets N2, RBX then gets N3, and so forth. So RAX is always going to have kind of this even value in the sequence, and RBX will have the odd value. We always have the previous two values available to us, and we can sum them and continue. So this looks great, right? We're now using just two registers in order to compute the Fibonacci sequence. Okay, so that's very good. I'm not going to run out of registers. I'm just repeatedly using the same two registers. So it's problem solved, right? Except where did these values we computed go, right? Now, maybe I didn't need to keep the intermediate values. Maybe I just do this a certain number of times in order to figure out a particular value in the Fibonacci sequence. But maybe not. Maybe I need to keep these things as I go. So I can't do this effectively just using registers, and so this is where memory comes in. All right. Now this is just an example of how we might approach this problem. You're probably looking at it and going, whoa, 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 that seems very wasteful. We'll see that it kind of is, but for the sake of argument, let's just go along with this, okay? So here we're doing the same thing. If you look at these instructions here, you'll see it's the exact same sequence of instructions that we just figured out, okay? What we've added, though, now is that after we find a value, and in the first two cases, we're simply assigning them, right? This is where we kind of initialize our Fibonacci sequence. So I could have just written those values directly to memory, but in order to establish a pattern, I just went ahead and instead just inserted a move instruction where we're moving the value of RAX to memory location 0x150. Okay, so this quad word, and so a quad word is 4 times a word, which is 4 times 16 bits. So this is our 64-bit value. This is being written out then to memory location 150 in hexadecimal. Okay, so then same thing here. We put the value 1 in RBX, and that gets written out to memory. So now at location 0x150, we would find the beginnings, okay, of the 16 bits, or excuse me, 64 bits that we used to represent a 0, and at 0x140, we would find then the first byte that we were using to store a 64-bit 1, which of course is a bunch of zeros with 1 1 in it. All right, so moving on from there. So we've stored these two values. Then we do the add operation. Now RAX has the third value, and then we'll move that into memory. So at 0x130, we're then going to store 0 plus 1. We just computed, and so we'll have another 1. And then we continue with our sequence, RAX plus RBX. That's going to give us a 2. And then we in BX and RBX, and then we'll store that at 0x120. And that'll be a 2, and so forth. Okay? So when we're done with this sequence, we actually now have all of these values stored in memory, and so they could be used later. Right? And we did this using 2 registers. So this solves our register problem. We figured out how we can use memory to reuse the registers. Now this was just one way you could do it. You could manually shove the data out to the specific addresses you want if you're working at this level. Or we could utilize the stack, right? So we have these push and pop operations that automatically move the stack pointer for us, continuously recomputing the next address that's needed or where we should be putting data. It's going to, in this case, we're using push Q, so it's going to push 64 bits each time, the contents of a register. And so all I've done now is replace those move operations with these stack operations to push. So by the time we're done, then the stack has on top of it the most recent value in our sequence, and we could move up through the stack then, or down through it, whichever way you want to think of it. We could pull those values off and work backwards through the Fibonacci sequence. So this would also be a way of utilizing memory, utilizing the stack in order to reuse our registers. And this is actually a very common scheme. If there's a register that we want to use, but we don't want to lose permanently the value that was in it, we'll very often just push that data onto the stack, and then later on we'll pop it back off. Okay, and so this is actually not atypical of the kind of thing that we'll do in order to reuse our registers effectively. Now, this brings us to kind of an obvious point, and that is that, okay, this is great, but it's kind of tedious. Okay, you're not the first person to look at assembly instructions and say, yes, I'm glad they're not ones and zeros, but I do wish this was still easier to understand. Okay, and so I wanted to introduce a pretty important figure at this point. Her name is Grace Hopper. She lived from 1906 to 1992, and she's quite famous for being one of the early pioneers in computer science. In particular, she's famous, she's given credit for the invention of the modern compiler. And so as a mathematician and a physicist, I know she was a mathematician, I believe she was also a physicist, she got involved in computing pretty early, and she was one who advocated very early for this idea that, well, we should be able to write computer programs in a readable language. We should have computer programming languages that look like English. And in order for that to work, obviously, somehow that English must be translated into a language, specifically machine code, that the computer can understand. And so she advocated this idea of a compiler. She was key in the creation of a programming language that's still in use today, known as COBOL, which is a very, very famous language in the business world. And so she served on the group that helped to create both that language and the associated compiler and so forth. And so she's one of these figures from history that succeeded in a time when quite frankly, women were being kind of ignored and held down in many scientific circles. She managed to accomplish great things, even against those currents. And so she deserves a lot of credit, not only for her brilliance, but I think also for her tenacity and her ability to kind of swim against those currents and accomplish some wonderful things. We owe her a lot. So every time that you sit down and use a high-level language, reflect upon the experience you're having right now and that you will have for the next few months, okay, wherein you are looking at the nitty-gritty details of a computer, and recognize that she is one of the reasons you don't have to deal with those nitty-gritty details all the time. One of the premises for this class is that understanding those details, being aware of them, will give you great power as a systems programmer, as a programmer in general, but we don't always want to have to use that power. Okay, and modern compilers are one of the things that allow us to save a lot of time and energy, both mental energy and time in general, and we owe this to her. So I'm giving you an assignment at this point. I would like you to go to the Wikipedia article that I have linked right here on this slide. Okay, the others there is a reference for one of the for this picture actually. But these other two photographs, the second and third photographs, come from the Wikipedia article that I have cited here. I would like you each to go and read that article. And you need to consider this an assignment. This is a very dynamic person that I would argue deserved probably more respect early on. She got a lot of that respect later on in life. You see her here with President Reagan. I think she's being sworn in as a Rear Admiral in the Navy. So she did certainly become a person of profound influence. But again, she is very much a pioneer in two ways in computer science, both in terms of pushing the field, but also in terms of being a woman at a time, a woman in computer science at a time when there were some pretty silly ideas about whether or not that should be a thing. So please go and read this article. You will be quizzed on it at some point. I think you'll find it very fascinating. All right, so moving on from there, because we have this wonderful thing called a high-level language and a compiler, we can do similar things to what we just did, assembly language, using syntax that's much easier to read, right? So here we've declared two longs, x0 and x1, and so we can, these will be 64-bit values. We've assigned to those variables the values 0 and 1, and then we can use simple arithmetic looking operators in order to compute those values. Okay, so instead of move instructions, we get to say things like equals, okay, or assign 0 to x0 and so forth. We get to simply use the plus sign. That's rather sloppy of me. The plus sign instead of needing to say add, and we can specify which variable we want the result to be in, and so forth. And the compiler then does the work of figuring out, well, what is an equivalent set of assembly instructions that would result in these values and have the values that are needed in the end stored somewhere that they can be used. All right. Now, we haven't gotten this far yet, but if we were doing something like a Fibonacci sequence and we wanted to compute lots of the values for the Fibonacci sequence and store them for later use, we would probably not just rely on the stack. We wouldn't just rely on hand-coded memory locations. We would utilize, again, the compiler's ability to set aside memory for us and to keep track of it. Forgive me, there's a slight syntax error in this slide, so there, we'll fix that, and I will fix that mistake in the slides I post on Learning Suite. But here, for instance, we might just set aside a block of memory to store 100 values of the Fibonacci sequence. Oh, I have a second typo. I apologize. Store the initial values for, I guess, to initialize the algorithm here, and then utilize a loop. Okay, so we might be able to think through pretty easily these two steps and the part here where we're doing the arithmetic. What we haven't covered very thoroughly yet is, or are rather, the assembly instructions we would need both to execute a loop like this, And we've only just barely touched on the kinds of assembly instructions we might use to manage an array as we're doing here. So we will dive into those things further going forward. But I just wanted to instill in you the idea that the whole reason we can write neat code like this, neat not only because it's kind of cool, but also because it's literally neat to look at, it's nice and tidy, has to do with this idea of a compiler. So that's what we're accustomed to. We're now working our way up in terms of our understanding and the tools that are available to us to try to get to a point where we can look at code like this and have an intuitive feel for the kind of assembly instructions that will be generated. All right, so that's where I'm going to stop with this for now. And again, hopefully this presentation gives you a framework, okay, a paradigm, if you will, to start from in understanding the rest of the x86 instruction set as we will be studying it. So thank you, and until next time, have a good day.